So far we have discussed only normal form games, which is very nice to capture the interactions which are simultaneous. So for instance, everybody is playing, so has a bunch of strategies and they are picking their strategies at the same time, and then certain outcome happens, they get their utilities. It's something like a one-shot game. The moment you are picking your strategies, all the players are picking their strategies, the game ends. But there are some other kinds of games, and we have discussed one in the very beginning, that is chess, which are not getting over in one stage, and not all the players are playing at the same stage. It is called the multi-stage games. So we will, in this module, we are going to discuss about such games and how we can represent them. Of course, these games are richer than one-shot games, therefore we need a richer representation. Now, so certain things that we'll be discussing here, some new terminologies will be also introduced. So players in this context interact in a sequence, and the sequence of interaction or sequence of actions that they are picking is called the history of the game. Now in this context we are going to discuss one game. So at this point we are going to only discuss about finite games, but later we can also generalize it for infinite games. So this is called perfect information extensive form games. So let us understand these two terms. So extensive form because it has multiple stages. It's not ending in one stage. The perfect information thing will become more obvious when we discuss its counterpart, which is imperfect information. So the notion of perfect information means that you can actually observe the actions that has been made by the other players. That's the way it is perfect information. There are some games where the other player is actually playing some strategies or picking some actions, but you do not really know. So you do not have exact information what is the state of the game. So let's imagine the game of cards. You know what has been played on the table, but you do not know what are the hands of the players. So contrast this with a game like chess, where you actually know what are the pieces and where their positions are, even for your opponent. So that is a perfect information extensive form game, chess. But the game of cards is not perfect information extensive form game. So we'll discuss that later. Now these games are richer, so a kind of a friendly warning is that there will be more notation to capture this. There's nothing to worry about it, and we'll go over this sequentially and discuss all the notation. Let us start with an example. That's the easiest way to discuss. So imagine that a mother has two kids. The siblings, brother and sister. Maybe the brother is older and sister is younger. So the mother says that please divide, and gives two chocolates. And imagine that these chocolates are indivisible. You cannot cut it in multiple pieces. Either you'll have to give it the integral one chocolate to one person, or not give him or her. So the game goes as follows. The mother says that the son that you should choose which division you want to give, and the sister has to either accept or reject that division. So the brother can actually decide whether to give. So 2,0 means it keeps two chocolates, both the chocolates for brother, and no chocolate for sister. Okay. 1,1 means it is equally dividing, and 0,2 means it's giving the whole two chocolates to sister. Now in each of these outcomes, each of these stages of this game, so once brother has chosen his move, the second player, that is the sister, has the choice of accepting or rejecting that proposal. Now the point is, the mother has said if there is any kind of dispute, so if a sister rejects your choice, then I'm going to take away both the chocolates and nobody will get anything. So in all these reject cases, everybody gets zero payoff. They get no chocolates. But if the sister agrees to it, then they get whatever the proposal was. So the brother has proposed 2-0, then brother's utility is 2 and the other person's sister's utility is 0. So that's the description of the game. And you can see that I have already drawn it in the form of a tree, because this game is always going to be a tree-like. Every time the player who is playing at a given node has a finite number of strategies, finite number of actions that they can take, not strategies. We'll come to the point what is the difference between action and strategies. And whenever it takes that action, the next player moves. So how do we represent this, formally capture this? Of course, to represent this game, we need the set of players. So that is the first thing that we have here. We also need the set of actions, which is the collection of all possible actions. So in this context, maybe you can collect together all the actions 2, 0, 1, 1, 0, 2, and also the actions of the sister. That is going to be one big set which contains all the actions. History, so this script H is the set of histories, and this is a little non-trivial. Let's go over it slowly. So this is the set of all sequence of actions of all the players. Of course, it has to contain the empty set, the point where it started, the origin. It also has to satisfy this following condition, that if a particular history is in that set, then all the subsequent H prime which starts from that origin, from the root, must also be in that H. So if you are looking at any arbitrary tree, let's say, and you have a particular history, so this history is considering all the intermediate actions, then any sub-history, so if this is H, then this should be H prime at this point. So all such H primes which are subsequences of H must also live in that history. There are some special histories which are called the terminal history, so where you actually end the game. So this is a finite extensive form game. That's what we are going to discuss first. So formally what it is saying, that you have a sequence of actions until this stage t-1. It is going to be terminal if there does not exist any other action in your action set, such that you can have this new action, so just appending that action to the previous history H. So you cannot find any action with which you can put this into the history. So if that is the case, then it is a terminal history. You cannot really have anything more than that. You cannot append to this history anything. So to denote that this terminal history, this terminal histories are actually special. We'll discuss why it is special. So to distinguish that, this set of terminal histories are denoted by this symbol Z. So this is the set of all terminal histories. The next entity here, this script of X, is the following. It is actually telling you what is the set of actions at a particular history. So of course, for the terminal histories, you don't have any actions. Terminal history is where the game ends. So none of the players will have any actions available at that point. For only the non-terminal histories, so H minus Z, this function X is actually mapping from all those non-terminal histories to the subset of all the actions, to the set of all subsets of A. So this is essentially, so if you just put let's say this script X of a specific H, which is a non-terminal history, then it will give you a set, maybe A0, A1, A2. So at that history, let's go back here. So maybe at some point, if your history is 1-1, that is in this part, you have two actions available. So so maybe we can write x of 1, 1. This is A and R. There are two actions that are available. So that's the the understanding of what we mean by this script X. So this function P is a player function. It is telling us who is going to move at that stage. At any non-terminal node, which player is going to play. So in that previous example, if you just put the same terminal history, so P of 1,1, which is the non-terminal history, is going to be 2 if we call sister to be the player 2. And of course, these utilities, and this is where the terminal histories are special. The utility is only defined at the terminal histories. In the intermediate histories, you don't really define, you don't have any utility, the game has not ended. So once the game ends, you have a utility function which maps this terminal histories into the set of real numbers. So this is the utility for player I. So now is the crucial definition of strategy. We have seen this in some form when we discussed the chess game in the beginning of this course. So let's do it formally here. Now we have all this notation available to us. Now the strategy for a player is defined as the complete contingency plan, as we have said before. So in this extensive form game, perfect information extensive form game, it is the tuple of actions at every history where the player plays. What we should remember is that strategy is this the complete plan for that player. So as it says, that it enumerates potential actions a player can take at every node where this player can play, even though those some of those combinations may never occur together. So I think it's better to explain this strategy using one example, the same example that we started with in this module. So it's very clear that player 1 and player 2, so player 1 is the brother, let's assume that player 2 is the sister. The actions that are available, here we are collecting all of them. We have already said that this is the action set. Just we are using the same A here and here, but I think that is clear from the context. Now the histories. So history should contain the null history, that is where the game starts. So maybe this is the history which is null. Then you have several sequences. So 2,0 that can be a history. 1,1, 0,2 are the histories, and you have also 20, A. So that is this path. So at this node, you can think of that as the history of 20, A. Similarly, 20, R, and so on until the final one here. The terminal history is, of course, those histories where you get this utility. So the leaf nodes. So this except the first 4, everything else here is the terminal history. Now you can decide what is the action set, action picking set. When you are in this histories 20, 11, and 02, which are the non-terminal histories, at that place the actions are A and R. And now you can also define what are the players. So player at the beginning is 1, and in all the other non-terminal history, player 2 is the player, sister. Now you can define for all the terminal histories. So there are 6 terminal histories in this game, and for all those terminal histories, you can define what is the utility as given here. So here I have written only those utilities where it is non-negative, non-zero. For all the other places, it is 0. Now here comes the interesting part, that the strategy. So strategy for player 1, because this player has only, so the player is playing only at one place. So it is only playing when the game starts. So therefore, its strategy is either to play 20, 11, or 02. So this is just these 3 possibilities. But if you look at player 2 is actually playing in multiple places, depending on which history has happened. The player player 2 can actually choose the strategies accordingly. So therefore, the strategy will not only give the action at any given history, it should give the complete map that at any non-terminal history what should happen, what should be the action of that player. And that will mean that if this player is playing in these three places, in all these places their actions are A and R, and therefore the strategy for player 2 will be represented by this tuple AAA, which means that in all those cases, in all those non-terminal histories, in all these places, it will play A. And there could be several other possibilities. So like AAR, this means that it plays in the first two non-terminal history, it plays A, in the last it plays R, and you can fill this up. So this is actually giving you the complete contingency plan for player 2. No matter whichever non-terminal node you are ending up with, you will still have a plan how to play in that game. So we have just defined that the strategies for player 1 and 2 are given by these sets S1 and S2, right? For these two players, S1 and S2 are the two strategies. Now the normal form game is kind of a flat representation of the whole game. You have the strategies all at once, and if you simultaneously pick this, then what will be the outcome? So that way we can also represent the same game. So on the columns, on the rows, we have represented the strategies of player 1, and on the columns we have represented shown the strategy of player 2. And once a particular pair of strategies, the strategy profile is chosen, then you know the complete tracing of this game, and you come to the terminal node, and whatever is the utility, that is the utility that you will get in this normal form game. Now since you have transformed this the perfect information extensive form game into a normal form game, you can use all the notions of the normal form game. For instance, you can talk about whether there exists a Nash equilibrium. What are the pure strategy Nash equilibrium in this game? Actually, there are many. So you can actually think about what are the Nash equilibrium. So maybe just by inspection you can see that this is a Nash equilibrium. Interestingly, this is also a Nash equilibrium. This is also a pure strategy Nash equilibrium, and there are many more. I'm not going to list all of them. But if you look at this games carefully, there are certain Nash equilibrium which are not really making much sense. What are they? Let's say we talk about 20RRA. So that was this one, this Nash equilibrium here. So let's say this is a Nash equilibrium. Let's go back to the game where we are playing this. So 20 and RRA, so which means that you have 20. The player 1 has played this action 20, and the Nash equilibrium is RRA. So let's say at this point, so let's say brother has actually given a choice of 1, 1. Why should the player actually reject it? Because this is going to give that player 0 payoff, while by accepting it could have actually got something positive. So it is not really making sense for any rational player to do this kind of a action, even though it is a pure strategy Nash equilibrium. So similarly, you can also think of the other one, 20 RRR, so which means it rejects everything. So quite interestingly, this is also a Nash equilibrium. So RRR, and the first player is actually choosing 2, 0. So again, the same question arises that if you have 0, 2, where player 2 is actually getting both the chocolates, why should it at all reject it? It should be making more sense to accept that, because that is going to give that player strictly a higher payoff. So even though these are Nash equilibrium, it is not really it's not capturing the fact that they can observe the game completely and therefore take this action. So it's not a credible equilibrium, if we want to call it. It does not have the capability of predicting the outcomes because no rational player will ever play that game, that kind of a strategy when it reaches that stage. So, so we need some sort of a new equilibrium concept, and we are going to discuss that in the next module. This is not good enough. This representation itself is not really very succinct. It's repeating all the utilities quite many number of times, and the representation wastes a lot of space. Maybe the representation, if you look at in a tree-like format like this, it is much more succinct representation of an extensive of a sequential game. So therefore, due to various reasons, we won't transform, even though the transformation is possible, this extensive form games into normal form games. Because neither the representation is meaningful, nor those equilibrium concepts. We'll have to develop new equilibrium concepts and new representation techniques for these games.